environment. Okay, let's do another problem. A well-insulated bucket contains 150 grams of ice at 0 degrees Celsius. If 20 grams of steam at 100 degrees Celsius is injected into the bucket, what is the final equilibrium temperature of the system? Is any ice left afterward? You see, you need to understand, visualize the problem if you want to do it. What is happening here? We have 20 grams of steam at 100 degrees Celsius is injected into a bucket. What is the final equilibrium temperature of the system? Now, what is contained in the bucket? A well-insulated bucket contains 150 grams of ice at 0 degrees Celsius. So it is into this ice that you inject the steam. Now, can you tell me what are the processes that happen there? Well, first of all, steam at 100 degrees Celsius is going to condense to water at the same temperature, releasing an amount of energy. Then, water at 100 degrees Celsius is going to come down to a lower temperature. We don't know what that lower temperature is. We are supposed to find that lower temperature. Now, if the lower temperature is 0, that means there is still some ice left there. If all the ice melted, then after melting, the water will increase its temperature to this equilibrium temperature. So we will assume that all the ice has melted, and the melted ice now increased its temperature to that equilibrium temperature. Okay, let's start by talking about it. Steam at 100 degrees Celsius condenses to water, releasing a quantity of heat. What is the quantity of heat released by steam at 100 degrees Celsius when it condenses to water at the same temperature? Q1 equal to mass times latent heat of, what's the mistake I have here? Vaporization, not LF, because steam is condensing to water. It must be L sub V. I'm not making the correction here, you need to make that correction. Q1 equal to mass times L sub V. That will be 0.02, 20 grams of steam, 0.02 kilogram times, I have used the right value for L sub V here. Although I wrote LF here, I have used the value of L sub V here. That is 2.26 times 10 to the 6, and that is 4.52 times 10 to the 4. Let's do it on a graph. Where will that look on the graph? We have steam at 100 degrees Celsius here is all the steam condensed to water at the same temperature here. So the amount of heat liberated is 4.52 times 10 to the 4 joules. And now, let's assume that theta is the equilibrium temperature. That means somewhere above 0. Let that be here. Let this be theta. We don't know what value it is. That means this water at 100 degrees Celsius here is going to cool down to that equilibrium temperature. Right? So, if theta is the equilibrium temperature, this water at 100 degrees Celsius cools down to theta degrees Celsius here, releasing an amount of heat. See, this time there is a change in temperature. What is the amount of heat released? Mass times specific heat of water times the change in temperature. Well, mass is 20 gram, that is 0.02 kilogram. specific heat of water is, what is it? 4180 joules per kilogram per Kelvin. What is the change in temperature here? The temperature is changed from 100 degrees Celsius to theta, so that will be 100 minus theta. So that will be mass times specific heat times the change in temperature is 100 minus theta, and I calculated that as 0.02 times 4180 is 83.6 times 100 minus theta. That is the change in temperature during that stage. There you are. It's from here to here. That is 83.6 times 100 minus theta. And now, we have now reached the equilibrium position from this side. Let's now start from the ice side. Well, if the equilibrium temperature is greater than 0, we then assume that all the ice has melted. Is that right? Let ice at 0 degrees Celsius melts to become water at 0 degrees Celsius. That is the first stage. All the ice first has to melt. So ice at 0 degrees Celsius melts to become water at 0 degrees Celsius. What is the quantity of heat absorbed during that time? It will be Q3 equal to mass of ice times the latent heat of fusion of ice. Now, mass of ice is 150 gram, which is 0.15 kilogram, times latent heat of fusion is 3.34 times 10 to the 5. That is 5.01 times 10 to the 4 joules. Now, that will be represented over here. All the ice at 0 degrees has now become, water at 0 degrees. Ice has changed to water by absorbing this much amount of heat. And now, this water needs to go up to the equilibrium temperature so that both meet at the same temperature. This water at 0 degrees heats up to theta degrees Celsius. What is the amount of heat absorbed during that time? Can you do that on your own? Q4 is mass times specific heat of water times the change in temperature. What is the change in temperature during this time? It will be theta minus 0. From 0 it increases to theta. It will be theta minus 0. So mass is 0.15. Specific heat of water is 4180 joules per kilogram per Kelvin. The change in temperature is theta minus 0, which is theta itself. So I can multiply these two numbers and then multiply by theta. It gives me 627 theta is the heat absorbed during that time. Water increases from 0 degrees to theta. There you are, 627 theta. Now, if you look here, the green lines represent the amount of heat liberated, and the red lines represent the amount of heat absorbed. The total heat liberated must be equal to the total heat absorbed. Alright, let's do that in the next page. Total heat lost by steam is this quantity plus this quantity. There you are. And the total heat absorbed by ice is this quantity plus 627 theta. There you are. And these two quantities must be equal to each other. Heat lost equal to heat absorbed. That means 4.52 times 10 to the 4 plus 83.6 times 100 minus theta, that quantity, equal to 5.01 times 10 to the 4 plus 627 theta. Well, this is now a simple equation in theta. You should be able to solve for theta on your own. I have done that anyway. Distribute these numbers. I produced that. So the only change in this step is 83.6 times 100 minus 83.6 theta. And now leave the numbers on this side and take the theta values on, well, theta values on one side. What does that give you? 627 theta is on the right side. Move that negative 83.6 theta to the right side. The right side becomes 83.6 theta plus 627 theta. And move all the numbers to the left side, and that's what you get. And now simplify that. You get 3460 equal to 710.6 theta, and therefore theta equal to 4.87 degrees Celsius. Well, because you got a value for theta as greater than 0, you can say all the ice has melted. If all the ice has not melted, you would have gotten a negative value for theta. And if you had a negative value for theta, your conclusion is not all ice has melted. The method of the problem will remain the same. Alright? This is a very important type of problem. I want you to practice this one more time on your own. Alright.